we start by going to our model wizard. For this work, we'll be using a 3D space dimension. And for our physics, we'll be using under ACDC, locate electromagnetics and mechanics, and we add the rotating machinery. All right. Also, we'll also add mathematics, ODE. Look, under ODEs, we select the domain ODEs, which we add. And the slight change that we're going to do here is just to change this units, custom units to this. Then we move to steady. We'll select a stationary steady. And it takes us to our Comsol interface here. So our first step, as usual, is to add our parameters. But with this work, we're going to load our parameters from file. So under parameters, we select load, and that will be the PM Moto 3D parameters. Which is added. Also, what we'll do next is to go to component 1 and under geometry, also locate the settings. So under, we're going to import okay. And browse to import this file. Import this PM Moto 3 file. That's our geometry. Later, I'll make a separate video on how to create this geometry on your own. So locate the geometry. Go back to form union and We locate the form union assembly section. And we select as form and assembly. We check this create imprint. We check this box and build a so let's look at the wireframe rendering as well of this geometry. Let's proceed to define our materials. So material first is to add built-in air. Then move to AC/DC. Select the soft ion without losses. Also, we add to components. Then we also look for add magnetic materials. And we have sintered. And we have to, let me widen this place so you can actually see. Okay. So this is the material. So under hard magnetic materials, we have sintered NdFeB grades, that are the Chinese standards, and what we select is the N50 NdFeB, Nobleon ion boron. So it has Nobleon ion and boron. So that's what we select. And last but not the least, we add aluminium. And not forgetting copper, as well as structural steel. Now that we're done selecting our adding materials, now we go to selecting the domain for each of these materials that we've added. So we'll first start with a soft ion without losses, and the domain will be geometric entity level should be domain, and select for of so this side is section for the soft iron without losses. So when you select this, how this part should be indicated. And locate the material content for the electrical conductivity. I want us to make some few changes. This should be 1. Okay, the value of this should be 1. Okay, this is left that way. Let's move to the next material. That's a sintered niobium iron boron. Label, let's change this label to magnet. And domain is 14. Also relocate the material contents for the electrical conductivity. Change the value here to 7 exponent 5. Relative permittivity is 1. Required permittivity is 1.05. Change this to 1.02. That's the recoil permittivity. And the remnant flux density is changed to 1. Let's move to the next side. That's the aluminium. And select the domain as we did for the other ones. Let's we select the domain 1 to 3 only. So this side is the section for the aluminium. We'll move to the next part. That's the copper. Copper is domain 7 to 9. Then move to structural steel. And for that one, select 13, 15, Second only. You can now proceed to set up the physics. So we're done with the parameters, the geometry, and adding the materials as well. Now we can move to selecting the physics and the rest. So with the physics, what we'll do is we'll select the rotating machinery. That's where we're starting from. We look for the discretization, and under the discretization, look for magnetic vector potential, which we want to change it to linear, as well as the magnetic scalar potential. We want to change it to linear. Also, look for the magnetic flux insulation. So under the physics, what we do is we locate under the physics section, locate domains, and we select magnetic flux conservation. And let's change this side to magnetic flux conservation of the air. And under the domain selection, paste the selections 5 to 6, 10 to 11 in the selection field. Okay. Once again, we go to domains and select magnetic flux conservation, and the label will be magnetic flux conservation for the ion. And under the domain selections, what we'll do is to select some range. So selection will be 12. This and be as I've done over here. So let's locate the constitutive relation B-H section, and under there we have magnetization model. We use a BH curve. Under the physics, we select Ampere's law, and the label will be Ampere's law for the stator core. Ampere's stator core. Okay. And under the domain selection, select this. Selection of before. Also, as we did for the other one, we locate a constitutive relation BH. And we select the BH curve. All right, so now that we're done for this side, what we'll do next is to do the definitions for the permanent magnet, the cylindrical coordinate. On the definitions, we look for coordinate systems and we select cylindrical system. Also, we go back to the rotating machinery under the physics domain. Select Ampere's law again. And that will be a magnet. Domains will be selected as domain 14. So under the coordinate systems, choose cylindrical systems to locate the constitutive relation BH section. And we select remanent flux density. Go to physics domain and we look for the coil. Coil will be 4 domains, sorry, be 4 domains 7 to 9. That's for the coil. We try to locate the conductor model. Okay, conductor model. And we select the homogenized multi-10. Coil type will be numeric. And the coil currents, look at this, number of turns as well. Coil currents, let's change it to 10 times sine omega times t. That means we have to change the number of ends to 1. Also change the equal conductivity to one of our parameters that we set already. So that will be the equal. Okay. So I think okay, so 1x is under the score 1. We have the geometry analysis. And under the symmetry specification, the core length application factor is changed to 2. Let's go to the input 1 and let's select boundary 3. So that's 143 for you. Under the geometry analysis, go to attributes and select output. So for the output, we have to select boundary 61. Let's see. Let's go to definition. Select the moving mesh. And you select the rotating domain. And select domains 10 to 12. And 14. Under the rotation angle, let omega roto times t. Okay, the axis, and we have to specify the rotation axis. So here it's 0, 0, but the z section is -1. Okay, so I think I'd like to pause here so we continue the rest of our work in another video. So if you follow to this point, please, like, if you have any questions, let me know. And I'm going to continue where I've left off in the next video. So I'll see you in the next video. So we will continue from where we left off from our first video. And the next thing to do is to add a force calculation. So we move to physics, and under domains, we have a force calculation. So for the force calculation, will be domain 12 and 14 only. As you can see, next is to add the cord fixing for the field. So for this gauge fixing for A field A, we want to add some boundaries to it. So let me add some boundaries to it. Let me add periodic condition boundary. And this will set the boundary to this positions. As you can see, set boundaries to these positions. And the type of periodicity using anti-periodicity to indicate these periodic conditions. And let's clear the selections for the second one. We just duplicate it and just put this boundaries 2 and 73 for the boundary. Positions. We'll also duplicate this periodic condition too. And clear the selection and select this boundary, this boundary, this boundary. So we're done selecting the boundaries. I think I missed one. It should be like this. Go to physics and fix boundary, and should have under the pairs have the sector symmetry. And we click add. We select identity boundary pair. Use case add.